Next, we go to example. We need to find zeta and omega n for this second order system. Let's say we have a transfer function here, 36 over s squared plus 4.2s plus 36. So how do we find zeta and how do we find omega? So basically what we can do is we can compare to this prototype of the second order system where we have s squared plus 2 zeta omega n plus omega n square over here. So we take this omega n square, so we compare with this equation here, the characteristic equation. We have omega n square equals to 36, so we have omega n equals to 6. And then we take the 4.2 and compare to this term. We have 2 zeta omega n equals to 4.2. So we know that our omega n is equals to 6. We have 2 multiplied by 6. We have 12. Zeta equals to 4.2, and zeta we have 4.2 over 12, which we can find it as 0.35. Okay, this is very simple. Just we compare the characteristic equation of the prototype of the second order system with a real value. And we have another example here. Alright, so again we can compare the value of this characteristic equation for each figure here. We take these values and then we compare with the prototype of this second order system. We have s squared plus 2 zeta omega n s plus omega n square, and then we can find the value of zeta as we calculate for these previous examples. And when we know the value of zeta, we can know the response. It is either under them, over them, critical them. So for example, for this question A here, we find that the zeta is equal to 1.155, which in this case is greater than 1. So when greater than 1, we say the system is over them. And then for this question B, we found that the value of zeta is equals to 1. We know that zeta equals to 1 means that the response of the system is critically damped. And finally, for the zeta value in the figure C, we found it to be 0.894, which is greater than 0 but less than 1. So we know that this zeta value corresponds to the underdamped response. We can also plot it into the S-plane. Let's say for this is the S-plane. We have sigma, we have j omega. For the question A, the value of zeta is actually greater than 0. We know that when greater than 0, the pole is located on the real axis. We have two poles of different location, means it is over them. For the question B, we know that it has the same poles at the same location. So two poles at the same locations means that we have the response of the system is critically damped. And finally, in figure C, we have the zeta value is less than 1, greater than 0, which is actually located on this position, where in this quadrant we have the response of the system is underdamped. Given the transfer function here, find the TP, percentage overshoot, TS and TR. Actually, what we can do is we just find the value of zeta and omega n. For the first parameter that we need to find is omega n, because omega n is simply omega n squared equals to 100. And then we can find the omega n equals to 10. And then we have 2 zeta omega n equals to 15. We know the value of omega n. We can substitute into the equation, and we have the value of omega zeta is equals to 0.75. So once we have the value of zeta and omega n, what we can do is just we take the formula for TP, formula for percentage overshoot, formula for TS, formula for TR, and then we can find all the parameters that have been asked in the question, and you can get all the values as shown in these slides. So you can try it by yourself. And the next example is we need to find TP, percentage overshoot, TS from the pole allocation. So this example is a little bit different from the previous example. Given that we have two poles here, which is located at -3 plus minus J7 here, so we can find the damping ratio. Remember, the damping ratio is given by cos theta. We can find from this formula here, theta equals to cos theta equals to cos of arctan 7 over 3. Arctan 7 over 3. Tan is 7, and then this is the distance is 3. So we can find tangent arctan. We can find this value of zeta, which is in this case is 0.394. And then the natural frequency is the radial distance from the origin to the pole. So we have this complex number, which is given by -3 plus J7. So we can take the magnitude of this complex number, which 7 square plus 3 square, and then we take the square root, and what we get is 7.616. Again, when we found the value of zeta and we found the value of omega n, we can find other parameters, TP, percentage overshoot, TS, by just replacing all the zeta and omega value into this equation. So we can find the TP by taking the formula pi over omega d, which omega d is the damp frequency of oscillation given by this j omega d, which is 7 in this case. So pi over 7 equals to 0.449. And percentage overshoot, we can find it by replacing the formula by inserting the value of zeta that we have calculated, and we can find the value to be 26%. And finally, we can find the settling time by taking the formula 4 of sigma d, which sigma d is the value of these. Here is we have -3, so 4 over 3, which equals to 1.33 seconds. So this is the real final example for this subtopic of the characteristic of the second order system. So given that we have these rotational problems here, we have is inertia J, we have a spring K, and we have the discus damper D, and given torque T, and we rotate it by the theta T. So given the system shown in figure here, we find J and D to yield 20% overshoot and a settling time of 2 seconds for a step input of torque. So what we can do to solve this problem, first we find the model of these rotational problems here. You can find the model, so we skip all the steps to get the models, and we found that the transfer function gs is equals to 1 over j over s squared plus d over j s plus k over j. So the next step is that we can compare this characteristic equation with the prototype of the system, s square over 2 zeta omega n s plus omega n square. So what we have is omega n is equals to square root of kj, okay, and then we have 2 zeta omega n, which equals to dj, and we can find the value of zeta. And from the question, we want to have a settling time of 2 seconds. We want to have Ts equals to 2. So the specification is given. So we have 2 equals to 4 over zeta omega n. Or we can say that we have a zeta omega n equals to 2. We can compare the value 2 zeta omega n equals to 4 equals to dj, and what's next is that we can also compare the value of zeta to the value of equation 4.50 and 4.52 in this slide. for 50 and for 52, what we get is zeta we get equals to 2 square root of j over k. The question also said that it wants to have 20% of overshoot. So what we have is actually we have 20% overshoot. That implies of zeta equals to 0.456. So how do we know 0.456? Actually, we have the equation of percentage overshoot here. So this is the equation of percentage overshoot. When we know the value of overshoot, we can find the value of zeta. So in this case, we find the value of zeta to be 0.456. So given that the values that we have calculated, we can put it into this equation. So I think we have all the parameters sorted out, and from the problem statement we can calculate these values of k, and then we can find the value of d, and we can find the value of j each. Alright, so I think we stop here. So if you have any question, you can always ask me in the class or in WhatsApp. Alright, until then, see you in the next lecture.